Hello and welcome to a new chapter in Machine Dynamics 2, a chapter where we want to combine the knowledge on journal bearings with rotor dynamic models. And there are two rotor dynamic models that I would like to use in this chapter, namely a rigid rotor and the Jeffcott rotor. In this video, I will deal with the rigid rotor only and would like to derive the equations of motion and derive the equations of motion and try to solve them until the point where we see that now we have to discuss stability of the solution in the sense of whether the amplitudes, the perturbations grow until infinity, so become larger and larger and destroy, therefore, the equilibrium behavior, or whether the solution and the equilibrium position of that rotor is stable. So basically in this chapter there are two objectives when we study these two types of rotors. So for each type of rotor we will answer two questions. The first one is, what is the critical rotational velocity? This is the question of self-excited vibrations. Namely, we will study the homogeneous equation of motion and the solution of the homogeneous equation. And then what happens with the external excitation by an imbalance? That could be also always possible. And then we study the amplitudes and would like to know whether the amplitudes, so the displacements of the shaft, become too big, too large, so that the shaft would hit the bearing housing. These are the two fundamental questions, and first of all we need equations of motion. So in order to derive the equations of motion, I will consider a horizontal rigid rotor. And now it is very important to understand the setting here in this chapter, because there is one subtle difference to the previous chapter, namely the eccentricity E here. The eccentricity E does not refer to the displacement of the shaft within the bearing. It's not what we measured in the last chapter. The eccentricity E here, if you have a closer look at the equations of motion, is the eccentricity E due to an imbalance, due to the fact that the geometric center is not the center of mass, but the center of mass is somehow shifted by an eccentricity E with respect to the center or to the geometric center of the shaft. This leads then to, if we look at the center of gravity, this leads then to a circular motion. And if we look at the stationary circular motion, so assume we are at imbalance and at equilibrium, so the shaft has a fixed position in that bearing, but of course it rotates. Then due to this imbalance, the mass is here of the rotor is 2m. Then we will find an excitation by an imbalance or mass force of 2m e omega squared sine omega t. On the other hand, we still have here the displacements, or the accelerations in this case, or the derivatives of the displacements for the geometric center of the shaft as inertia terms. So part of the inertia is on the left-hand side, part of the inertia is on the right-hand side. The external forces are 2F, which is the dead load, and 2Fx, because we have two bearings. Now you might wonder that we call the mass, or that we introduce 2m for the mass of the rotor. Are there two rotors? And why we call the external force 2F instead of F, having simply F here. Well, if you look at this equation, then we have two bearings. For the other things, we just have one. We have one rotor, and so one dead load, and so on. However, well, if you don't like this, you don't have to follow that procedure, but it's one that you find in the literature here is, if you introduce the mass with 2m and the external force with 2f, then you can easily divide the whole equation by 2. And as then the equation becomes easier than to have a factor of 2 or always here for the bearings, and one sometimes forgets that factor of 2. This is a kind of simplified procedure, I would call it, or simplified approach that leads to the fact that you can drop the 2 here. So this would be the vertical direction here, the first equation with 2f pointing in the vertical direction. We are in space fixed coordinates here. And the second equation would be in the lateral direction, with again the inertia part with the bearing forces in lateral direction and with the effect of that rotating imbalance. And once again, E is the difference between the center of gravity and the geometric center of the shaft. In order to analyze these equations of motion, we will do 2 steps. First, we will transform these equations of motion in dimensionless form, because for the bearing, we always analyzed or most often at least, analyzed the dimensionless situation. So we want to introduce dimensionless quantities. And we would like to study perturbations. So I would like to introduce then in a second step perturbations from the equilibrium position. So first let me introduce dimensionless quantities. So what are the appropriate dimensionless quantities here? Well, for time, it's still the dimensionless time is equal to the rotational speed times physical time t. For the displacements x and y, we divide by the clearance as before. For epsilon, attention, again, that epsilon is with E here. It is not the eccentricity ratio anymore. It is the dimensionless eccentricity, let's call it like this. It's, again, E measures the difference between the center of gravity and the geometric center of the shaft, so between 2 material points on the shaft. It has nothing to do with our radial displacements anymore. They are hidden here. You can see they are well hidden here in the displacements x and y that are introduced, inserted, I would say, in the bearing module. And from that, E and gamma are obtained from these Cartesian coordinates. So E divided by C, and for omega, we use the classical result Cm divided by f square root omega. We will see, if we look at these equations, that that this is the correct form. Well, the equations, the dimensionless equations, are obtained by dividing with respect to f. So we divide the dimensional equations by f, and we introduce the dimensionless quantities. And for the derivative, we would obtain here, for the derivative with respect to time, we write the derivatives with respect to dimensionless time with a prime. So we would obtain omega squared here. On the left-hand side, we divide, of course, the whole equation by 2 to get rid of that. So we would have omega squared, we would have an m here, we divide it by f, so we have f, and when we switch to dimensionless x instead of dimensional x, we have to multiply, or we have to introduce instead of x, x bar times c. So in total, what we get here as a leading coefficient would be c times m divided by f times omega squared. And this is then abbreviated, as the quantity must be dimensionless, by omega bar, leading to an omega bar squared x double prime. 1 for the ratio of the force, you can see fx, f, we get that dimensionless force fx is the ratio of fx divided by x, and then 1 divided by the Sommerfeld number, which is a dimensionless quantity. So we replace the ratio fx divided by f by Sm times fx. And now for the last term, we replace E by epsilon. Then we have a C. We have Cm we divide by f, and we have the omega square leading to an omega bar squared, so epsilon omega bar squared, and then the argument of the sine function is simply tau, because tau is equal to omega times t. Same for the second equation. You can see the first term on the left side is transformed in the same way as the first term of the first equation, or as the term the first equation on the left side. For the bearing force, the same holds as before, so we have 1 divided by Sm f sub y divided by f, so that f sub y divided by f is replaced by f lowercase fy times the modified Sommerfeld number. And for the last term, well, the reasoning is the same as for this term here, so we get epsilon omega bar squared and the cosine of tau only. So this would be our equations of motion in dimensionless form. And now in this way we are able to introduce now the displacements delta x and delta y from the equilibrium. When we do this, there's one quantity that we will lose, much the same as if you consider the vibrations of a mass in gravity field and you set your level to 0, you will lose the inhomogeneous term of the excitation, the constant term in the excitation, the one here. That is balanced by statics. If we introduce displacements from the equilibrium, so-called perturbations, and we will look whether these perturbations tend to grow or not, we will lose that term here. We will replace, instead of x bar, we will use a mean x bar or equilibrium x bar plus delta x bar. So we will get delta x bar double prime here. And for fx, we introduce the linearized form, namely the damping coefficient matrix and the stiffness coefficient matrix. And this term here moves to the right-hand side. We had the damping and stiffness coefficients modeled as restoring forces with a negative sign, so they move to the right-hand side with a positive sign. All this can be seen on the next slide. Here you will see the results. So if you introduce displacements, perturbations from the equilibrium position, you will lose in the first equation the term with the 1. For the bearing forces, you consider the restoring forces on the left-hand side. They would be negative, and you introduce the stiffness and damping coefficients with respect to the first order derivatives, the damping coefficients with respect to dimensionless time. For the stiffness, you consider the stiffness matrix and multiply with the displacements. And here for the inertia part, you take the second order derivative with respect to dimensionless time of delta x and delta y. And this is our right-hand side, epsilon omega bar squared sine tau and cosine tau. If you look at that equation, then in this equation there appears as a parameter, you would say, well, perhaps there's only one parameter, the omega bar, but keep in mind that you have to compute the stiffness and the damping coefficients. And they depend on epsilon or on the modified Sommerfeld number. You can see that all these parameters can be transformed. So once you have, so if you fix all the other parameters, once you change the rotational speed, you will change by this also the modified Sommerfeld number, and you will change the parameter epsilon. No, you will not change the parameter epsilon. Attention. Also, I did this mistake. Epsilon here is not the eccentricity ratio. That clearly depends on the Sommerfeld number, also my fault. Epsilon is that imbalance distance, and that is really independent. That is completely independent on the other choices. No? Once again, epsilon here it relates to an imbalance, so dimensionless imbalance to the difference between the center of gravity and the geometric center of the shaft. No? Okay, so these would be parameters of the problem. Now, let's look at the self-excited vibrations. So self-excitation means we switch off that imbalance, so that parameter epsilon here, and we just work with omega bar, and thus also, of course, with the Sommerfeld number, with the damping and stiffness coefficients. And the right-hand side is set to 0, so we are looking at the homogeneous differential equation. Here it is. Well, if we want to solve such a homogeneous differential equation, we observe that it's a linear ordinary differential equation of second order, so a classical approach, even the coefficients are constants. They are not constant if you change the rotational speed, but for a given rotational speed, for a given Sommerfeld number, these coefficients will be treated or can be treated as constants. So the solution approach for such a linear homogeneous ordinary differential equation is just setting the displacements equal to some amplitudes times exponential lambda bar tau. So all the bars should indicate that these quantities here are dimensionless quantities. You know that this leads to an eigenvalue problem, so you insert the solution approach into the ordinary differential equation, and then you get an algebraic system for the amplitudes x bar and y bar, and according to the reasoning that you need non-trivial solutions to have any vibrations or anything, you will then get the equation that the determinant of the coefficient matrix should vanish, and this is the characteristic polynomial. Let's follow these steps. So we introduce the solution into the ordinary differential equation. For this we have to take twice the derivative here. Here we take once the derivative, and we arrive at the following equation. Let's just summarize the terms here. Right hand side is equal to 0. We have an algebraic equation that governs these two amplitudes, so we divide by exponential lambda tau, the whole thing, and then let's look at these coefficients. So the coefficient that are combined with x bar here are from the first column. Yeah? Let's look at the first row, first column of that equation. We have omega bar squared that is combined with x. After taking twice the derivative, we have to multiply by lambda bar squared. From the stiffness matrix we get our Cxx. We have to multiply once with lambda bar here. And from the damping matrix, from the stiffness matrix we take our K sub xx. Here it is. We move to the second column. Now to these parts that are multiplied by y bar. They are found in the second entry of these matrices, so 0. Cxy from the damping matrix, which is then multiplied by lambda bar, here it is, and kxy, here it is, kxy. Yeah? Second row of our coefficient matrix is composed by all the entries of the second equation that are multiplied by x bar. So in first position in this matrix, here it is 0, here it is cyx from the damping matrix times lambda bar, here is the entry, and kyx, here it is. And finally, those entries of the second column, so those terms that are multiplied by y bar, they are found in the second row, second column of these matrices. We have an omega bar squared here, second order derivative leads to lambda bar squared, omega bar squared, lambda bar squared. Then we have a cyy multiplied by lambda bar, here it is, and finally we have kyy. So this will be the equation. And again, non-trivial solution for the two amplitudes, x bar and y bar, are obtained if the matrix is singular and the coefficient matrix is singular if the determinant of that coefficient matrix vanishes. And this is an eigenvalue problem, namely for these values of lambda bar. Well, let's formulate that eigenvalue problem. Here you can see it once again. So we will look again at our linear algebraic system. What can be said about our characteristic polynomial? Well, the characteristic polynomial is of order lambda in fourth power, because the highest power you can obtain here from the determinant of that matrix in lambda bar is the fourth order. It's a fourth order polynomial. So we are looking for the roots of a fourth order polynomial. That's already difficult enough. And let's write down the coefficients. First, the coefficient A0, so the coefficients that are completely independent on lambda. Those are obtained by multiplying stiffnesses, namely for the diagonal elements kxx, kyy, minus kyx, kxy. So this one here. There is a notation A0 tilde. We will separate all the terms that include an omega bar here, well, which will be an omega bar squared because omega bar appears only in squared notation, or in second power. So for A1 are the terms in the polynomial that depend linearly on lambda bar. They are obtained by multiplying a damping term with a stiffness term. So a damping with a stiffness on the diagonal terms, there are two possibilities to do that. You can multiply cxx by kyy. Oh, that's the second entry here, okay. And kxx by cyy, that's the first term here. And for the off-diagonal term, so negative sign there, you can multiply this one, cxy by kxy, cxy by kxy, and then you can multiply kyx by cxy. Maybe you remark here that I noted cxy here instead of cyx. Why did I do this? Because I know from the previous video, from the investigations, that the damping matrix, that the coefficients of the damping matrix here are symmetric. So therefore I can write cxy instead of cyx. So we get kxy times cxy, the first one, and we get kyx times cxy, the second one. And again, I notice that there is no influence of omega squared here, therefore I call this A1 tilde. Next comes to A2. So the terms that are in lambda bar squared, or the coefficient for the terms in lambda bar squared. Terms with lambda bar squared are obtained by multiplying one term that comes from the inertia with a stiffness. So this is possible here to multiply by kyy and to multiply here also by kxx. We have no influence here on the off-diagonal terms, so that's it already. No. I did a mistake in thinking, too quick, because you also have the possibility to multiply two dampings, and you will get a lambda bar squared. And this is the rest of that entrance here. So you get here cxx times cyy minus cxy squared. I don't know why I wrote here cyx, that's cxy squared, but doesn't matter. So if you look at that situation, then indeed we find for the first time, we find the term in omega bar squared. So we notice this as omega bar squared a tilde 2,1 plus a tilde 2,2. And you see that a tilde 2,2 is an abbreviation for cxx times cyy minus cxy squared. And a21 is an abbreviation for kxx plus kyy. So the important thing is here to really show in the coefficients of that characteristic polynomial the influence of the rotational speed and therefore of omega bar. That's the reason why I introduced these abbreviations. I mean, these abbreviations make sense, or well, one could also work with these abbreviations instead of working with all these dampings and stiffness coefficients. But this special notation is due to the fact that I would like to especially point out the importance of omega bar here for the future analysis that I would like to carry out. Okay, let's move to A3. A3 is obtained by multiplying a stiffness term with the damping term, and now no chance for the off-diagonal terms with these dampings. The maximum order you would get here is lambda 2, lambda in second power. So therefore we get omega bar squared multiplied by cyy and an omega bar squared multiplied by cxx. And this is then written as omega bar squared A3 tilde. And so finally for A4 is obtained by multiplying the two inertia terms. So it's just omega bar 4. You could write there an A4 bar, but it is simply 1. So what you see is that these eigenvalues depend on omega bar, and don't forget they also depend on the modified Sommerfeld number. But if you take everything as constant in the modified Sommerfeld number except for the rotational speed, then you could say that the whole thing depends on the rotational speed. There's no influence of the imbalance anymore because we are studying the homogeneous equation. Now, of course, the next step would be, but we won't follow that step, would be the solution of that characteristic polynomial, determining the roots, and then concluding from the roots about the stability behavior of the solution. Namely, that the real part, as the roots lambda indicate exponential behavior, that the real part of all the roots is negative. Then we have decaying behavior. If there's just one root with a positive real part, then that root would destroy the solution behavior in such a sense that this perturbation would tend to infinity. That should be avoided. However, what should be also avoided is the solution of such a characteristic polynomial, because it's already of 4th order. That's difficult to do. And we would like to study the influence of certain parameters here. That's analytically infeasible. What would help us would be if we are able to draw some conclusions just on the sign of the real part of the eigenvalues by studying not the eigenvalues, so by not solving the characteristic polynomial, but by studying just the coefficients of that characteristic polynomial. So in the sense that the polynomial is fully characterized by its coefficients, so somehow in these coefficients the information on the roots and therefore on the sign of the real part, which is much less, it's a qualitative information, it's not a quantitative information, must be hidden. And how this is done, how this is hidden in these coefficients, will be shown to you in the next video. Thank you for watching.